A matrix can be used as a map that transforms one vector into a different vector. In order to keep the dimensions of the vector consistent, the matrix must be a d by d matrix if we're dealing with a d-dimensional vector. When we translate ordinary matrix notation into index notation, we have to make a choice about how to arrange the indices on our matrices. The Einstein summation convention says that we should tie upstairs and downstairs indexes together. But if we have an I index that's free on the right-hand side and U upstairs I, then there should be an upstairs I index on the left-hand side. And oh no, I seem to have made the cardinal mistake. I've written too many I indexes. So let's replace the I on the vector V with a K, and the corresponding contracted index on the matrix with a downstairs K. Now the remaining I indexes are free indexes, and they should match. Just like in any equation, the equation should balance. To reiterate, a matrix transforms a vector into another vector. The free index labels must appear in the same position, both up or both down, on both sides of an equation. Dummy indexes do not have to reappear on the other side of an equation. You can think of them in some sense as being absorbed. A natural follow-up question is, what's going on with the weird spacing on the matrix indexes? Could we just write them in any order, have the J downstairs come ahead of the I upstairs, or even have them lined up vertically? Well, of course we could do that, but in general we don't. The ordering of the indexes matter, and the different orderings correspond to different matrices in general. On the other hand, if the ordering is irrelevant, if M upstairs I downstairs J is equal to M downstairs J upstairs I, then the ordering can be gotten rid of entirely and we can just stack the indices on top of each other.